Hello and welcome. Imagine materials that don't exist in nature, materials engineered atom by atom. What if these materials could bend light, sound, or other waves in ways we once thought impossible? This isn't science fiction. It's the fascinating world of metamaterials. So what exactly are metamaterials? They are artificial structures designed to have properties that go beyond the materials they're made from. Think of it this way. Normally, a material's properties come from its chemistry, like gold being shiny or rubber being stretchy. But metamaterials get their unique abilities from their incredibly precise internal structure. They're often built from repeating patterns, much smaller than the wavelength of light or sound they're designed to influence. The real magic happens when a wave, like light, hits these tiny structures. By carefully arranging these subwavelength elements, often tiny metal or dielectric resonators, scientists can control how the wave interacts with the material. Specifically, they manipulate its effective permittivity, which is its response to electric fields, and its permeability, its response to magnetic fields. This level of control leads to some truly exotic effects. The most famous is perhaps a negative refractive index. In simple terms, this means light bends the wrong way compared to how it behaves in any natural material. This opens the door to wild concepts like perfect lenses that could see incredibly small details. Metamaterials can also be anisotropic, meaning they interact with waves differently depending on the direction, or they can be tailored to perfectly absorb or reflect specific frequencies. Where could we use these amazing materials? The possibilities are vast. In optics, we're talking about invisibility cloaking, guiding light around an object. While still mostly theoretical and limited, the concept is mind-blowing. Superlenses could revolutionize microscopy by seeing details smaller than the wavelength of light itself. We could also see miniaturized optical circuits. In acoustics, think about sound cloaking, or focusing sound exactly where you want it. Imagine targeted noise cancellation built into the structure of a room or vehicle, or much higher resolution medical ultrasound imaging. Mechanically, metamaterials could lead to incredible vibration-damping materials, protecting buildings from earthquakes, or making aerospace components more resilient. They could also form the basis for new lightweight, yet incredibly strong materials. Even in energy, metamaterials offer potential for more efficient antennas for communication and energy harvesting, or better ways to manage heat flow in electronics. Of course, there are challenges. Creating these intricate structures, especially at tiny scales needed for light, is difficult and expensive. Making them work over a wide range of frequencies, rather than just one specific frequency, is another big hurdle. But research is moving fast. New fabrication techniques like advanced 3D printing are making things easier. The future might bring tunable metamaterials that can change their properties on command. Metamaterials represent a fundamental shift. By designing structure at the nanoscale, we're learning to manipulate waves, light, sound, heat, in unprecedented ways. We are, in a sense, starting to design reality itself, blurring the lines between science and science fiction. It's a field to watch closely. Thanks for tuning in.